Good morning, everybody. So today is more lecture. It was on the schedule actually, as I knew I was going to be lecturing today. Next week's lab day says lab, and depending on where we are in lecture, we might actually have actual equipment. I'm going to keep you in suspense because I actually don't know where I'm going to be as of this Thursday in terms of our lecture content. Kind of depends on how many tangents I go on, that kind of stuff. So we'll see what happens. I'll prep you more about what's going to happen next week when we get closer. But quantum mechanics, relativity, all this modern physics stuff, really we need more than half of the semester to get through the content, and we don't. So we don't have the equipment to do the experiments, and so we tack on extra lectures. So probably about an hour and a half today. I don't believe in lecturing for 3 hours at a time in labs, but try to keep it at that hour and 15, but I'm going to miss that mark by just slightly today. So just so you know what you are up against. We left off last time talking about the photoelectric effect, and it was a bit esoteric, and I knew that I didn't do any direct application or any of that kind of stuff, so I want to do some examples. I want to lay out some of the equations for it, and then tell you why it's important in your everyday life. It was important to physicists because it was the beginning of quantum mechanics, right? Einstein won his Nobel Prize for his explanation of the photoelectric effect. But beyond that, we can take advantage of this effect to do some really, really cool things. So let's lay out. I had this all set up and ready to go. You guys saw it. It was all ready to go. Let me reboot this. Best laid plans and all that kind of stuff. Come on. Quit out. Maybe that's the problem. It doesn't want to clear it. Now will it work? Please work this time. And no. Oh, it did come back. Can you guys see that? Yes. All right. I showed you a video last time, kind of how the electron was getting over the fence, so to speak, of the photoelectric effect. There was a photon that came in with an energy. So this HF is the photon's energy. This phi right here, this is called the work function. And it's the amount of energy that a charge needs to be able to leave a metal. So if your photon gives the charge enough energy to get off the metal, it can just barely get off, right? If the photon energy were equal to the work function, everything would be even. You would just barely make it to the top of the fence. Anything extra that the photon gives will turn out to be kinetic energy. Will end up being the energy of the charge moving off and away from the metal. I've got some work functions of various metals up here just to show you, right, that different metals have different amounts of energy that are required to get charges to come off of them. But the key thing here is understanding the relationship between the energy of that photon and the work function of the metal. You'll notice, though, that we are giving the work function on this table in a funny unit. And this funny unit is called the electron volt. It's a really unfortunate name because it has the word volt in it, which brings us back to electric potential that we studied before. The electron volt is not a unit of potential. It's a unit of energy. So like a joule, it's energy, but it's not a joule. The electron volt is a redefinition of the amount of energy we have. It's equal to 1.6 times 10 to the minus 19 joules. the amounts of energy that charges have on metals is really, really tiny. It's just a really small number. And so to avoid having to use really small numbers all the time, in quantum mechanics, we redefine our energy scale in terms of this new one, electron. So an electron volt is part of the SI unit system. I know you've learned this entire time, you always want to get back to joules or something like that, right? But an electron volt is a unit of energy. It's just as valid in the SI unit system. There is a conversion factor that goes between an electron volt and the amount of joules. Planck's constant, remember the energy of a photon was equal to Planck's constant times its frequency? That constant, Planck's constant, can be written in two different forms, two different numbers. 6.626 times 10 to the minus 34 joules, which is like a super joule times a second, is a really, really tiny number. But it also is written, and this is a bit of a shortcut for our mathematics, as 4.136 times 10 to the minus 15 electron volts times seconds. So you'll see both of those constants. They are the same constant written in a different unit of energy. And the electron volts unit of energy scales better with quantum mechanics, which is the science of very small amounts of charge and very small amounts of momentum, that sort of stuff. Okay, so I'm gonna give you an example of working kind of in this here just a bit, but just so you realize that we are rescaling our energy a bit here by using the electron volt, and you're gonna see that sort of moving forward, especially as we get into nuclear physics. We'll be talking about electron volts a lot. Okay? All right, so photoelectric effect mathematically, let's do an example of working with this funny unit of electron volts and knowing when to do it and not, okay? So here in this problem, okay, they're telling us the wavelength of light that we have shining on the metal, and we've observed that we get some kinetic energy of these charges coming off of this metal, but notice they've given us that kinetic energy in units of electron volts instead of joules. So the electron volt is a valid unit of energy. I say valid. I consider imperial units invalid in this context, right? Okay? But the EV is an SI unit. We just have to be careful about how we use it. So how are we going to find the work function and then these other things that I haven't told you about yet? Well, we know in the photoelectric effect that the maximum, the most kinetic energy that any charge can have is going to be equal to the photon's energy minus the work function. So if we want to know what the work function is, we are going to need to take that photon energy and subtract our kinetic energy. That's an algebraic manipulation, right? I move the work function over, add it to both sides, I subtract the kinetic energy for both sides, I end up with this statement right here. But the problem is they haven't given us the photon's frequency. They've given us the photon's wavelength. So how do we get from one to the other? How do we trade frequency for wavelength when it comes to light? What was it?
Speed?
Yeah, right? It's that wave speed. The speed of a wave is equal to its wavelength times its frequency. And since we're talking about light, we know that that speed has to be the speed of light. So that means that we can find the frequency by taking the speed of light and dividing by the wavelength. Or, when it comes to the energy of a photon, it can be Planck's constant times the frequency, or Planck's constant times the speed divided by the wavelength. All right, so we can go ahead and start putting this all together. My work function is going to be Planck's constant times the speed of light divided by the wavelength minus my maximum kinetic energy. Again, my maximum kinetic energy was given in units of electron volts. And so that's a kind of a dead giveaway as to which version of Planck's constant I'm going to want to be using. I can't subtract, like if I get joules over here and subtract off an electron volt, I can't do that. That's not allowed. That's subtracting apples and oranges. So I need to get this and this to either be the same. They could both be joules, or they could both be electron volts. So we either convert the 1.31 into joules and then use Planck's constants in joules times seconds, or, and I'll show you this, we're going to use Planck's constant in its electron volt times seconds form, and you're going to see how it's all going to work out. So let's do that. So my work function is going to be, there we go. Planck's constant. I'm going to use the 4.136 times 10 to the minus 15, and I'm going to put the units in so you can see how this all works out. So I'm going to put it in its electron volt seconds form. Speed of light, 3 times 10 to the 8 meters per second, so I'm going to put that one in standard units. And then I'm going to divide by 350 times 10 to the minus 9 meters. You'll notice I'm still putting things like nanometers, right? I'm writing it out as the full thing times 10 to the minus 9, that sort of stuff. Getting it into standard units of meters. Okay, so that's my first term right there, minus 1.31 electron volts. Okay, so what happens here, let's take a look at the speed, the meters per second in the meter. So if I got a meter on top and a meter in the denominator, what happens? Those cancel out, don't they? Right? So meter over meter gets a cancel, okay. And then I have an electron volt times a second divided by a second. So what happens to those seconds? They also cancel out. And I'm left, you can see there, I'm left with electron volts, right? If I had used Planck's constant in the joule seconds form, I would have been left over with joules here, but then subtracting off electron volts, right? So I guess the point I'm trying to make here is be careful, right? Make sure that you might want to put units in whenever electron volts are involved, just to make sure that you've got the right units in places. So I put this all into my calculator now, and I got out 2.24 electron volts. So it was 3.55 in that term over there, minus the 1.31 gives me that. So now I know the work function for this potassium metal, okay? I knew how fast electrons were coming out, what their kinetic energy was. I knew the energy of the photon coming in, the difference between those things was going to be the work function. Okay, then they asked me for something called the cutoff frequency and the cutoff wavelength. In the photoelectric effect, remember, that certain frequencies can't do the photoelectric effect. It's only the ones that have higher energy, higher frequencies that can do it. The cutoff frequency and the cutoff wavelength is that limit. Like what frequency will cause the photoelectric effect to happen, but then any frequency below that, it doesn't happen. It gets cut off at that point. So to find that, you set the kinetic energy max to be equal to 0. This is the limit, right? This is, once we hit that limit, right, and there's no kinetic energy left over, if we haven't hit it, then it's not going to make it over the fence. So with the kinetic energy equal to 0, we get photon energy minus work function, or photon energy equals work function, or the cutoff frequency is going to be the work function divided by Planck's constant. And then the cutoff wavelength, since the wavelength and frequency combined are the speed of light, we can go ahead and find the wavelength that corresponds with that frequency by taking speed of light, divide by the cutoff frequency, and we'll get that. So this is our cutoff frequency right here, and then the standard swap, that top equation, solving it for the wavelength, I can find what the wavelength is if I know the frequency. So to calculate the cutoff frequency, I'm going to take 2.24 electron volts. Since that's my work function. And then what form of Planck's constant am I going to divide by? Look at the unit. Joules times seconds or EV times seconds? EV, right? I've got a work function in electron volts. So I'm going to use the 136 times 10 to the minus 15 electron volts times seconds. Again, my electron volts will cancel. I'll end up with an inverse seconds, which is a hertz, which is what I want. And this turns out to be 5.42 times 10 to the 14 hertz. Here's my cutoff frequency, and then my cutoff wavelength will be the speed of light, all divided by that frequency, which gets me a wavelength of 554 nanometers. That was a really bad 554. So I really do believe that the math here isn't terribly hard. We're dividing and subtracting. The sort of gotchas when it comes to calculating stuff with the photoelectric effect is the units that you're in, right? And you're using like really tiny numbers, right? 10 to the minus 15. So struggling to get your calculator to do that engineering notation and stuff can be a little bit daunting. Like this answer came out as 5.54 times 10 to the minus 7 in my calculator. But to express it in nanometers, which is sort of the natural thing for wavelengths, I had to do that, shift of scientific notation and all that kind of stuff. So there's all these little gotchas along the way, especially with units. So just be careful with your units. Otherwise, photoelectric effect is like this one thing in quantum mechanics that feels really straightforward, right? If I can add and subtract, I can do the photoelectric effect. I know that the charges aren't going to come off that metal if there isn't enough energy to do it. So why does this stuff matter? Where does it hit you in your everyday experience, and why are we learning about it? What you're looking at here is something called a photomultiplier tube. This is an invention that allows us as humans to capture a single photon and be able to measure the presence of that single photon. Think about that. Photons have very little energy to them. It's a very, very small amount of energy to measure with a mechanical device. I mean, granted, we already have photon detectors built in right here, right? But in terms of computers and things being able to detect the presence of light, those photons are just very, very tiny energy things. How do we get a signal from something that's so small? Well, photon comes in, it can knock a charge off via the photoelectric effect. And then we can keep taking advantage of the stuff we learned back in circuits and with electric fields and stuff. If we apply potentials across different plates, and every single one of these plates causes a photoelectric effect to happen, what we end up is with an avalanche or a chain reaction of photoelectric effects. Charge comes in, produces a photon comes in, produces a charge. That charge comes in, knocks some more charges off. They continue to cascade through this photomultiplier tube, and at the end, we've got a magnified, amplified signal that we can do something with in our circuitry. And since we know exactly how much energy we put into it at every step, we can work backwards mathematically to the original photon energy. And so, why is this important? Why would we ever want to detect individual photons? Does anybody know what this is? This is what's sitting almost right behind this. Okay? This is the detector that allows you to take pictures. Its sole purpose is to collect photons and turn them into a signal that is loud enough, big enough, amplified enough that the circuitry of your phone can do something with it, right? So we're talking about this technology we carry around in our pockets. and more or less like constantly streamed to the universe on social media, right? All comes down to the photoelectric effect and being able to detect the presence of photons. This is an array of photomultipliers, solid state ones, they don't have to be in two. But this sensor has a resolution, each one of those pixels is an individual photomultiplier taking advantage of the photoelectric effect and everything that it can do to take those pictures. This is a more rudimentary photoelectric effect device. This is the thing that you will find, you can still find them in remotes. Almost every television, DVD remote, cable box remote, something, right, has a little LED emitter in the end here, this little tiny light bulb that sends an infrared pulse towards the box that you're trying to control. More and more nowadays, these remotes are like a Wi-Fi or a Bluetooth signal, and I've noticed that they're a little bit less reliable than the infrared remotes. But what would happen is when you push a button on the remote, an invisible series of pulses, flashes, comes out of this LED. This is the thing that's sitting inside your TV or your box or whatever that's receiving those pulses of infrared light. It receives the pulses, converts them into an electrical signal via the photoelectric effect, which then can tell the device what it is you wanted to do. Or you want to do volume up, you want to do Netflix, what do you want to do, right? And you can control it all from the comfort of your couch. So does this mean that the quantum mechanics and the photoelectric effect is responsible for the obesity epidemic in America? No, okay. Have you guys seen those things where you have to sit on the couch and pedal the generator to make the TV work? I've always thought that we could get PE to happen in schools if we made all the kids carry their PlayStations over their heads, right? You get to play PlayStation for 15 minutes for every mile. You run your PlayStation around the track. No, I'm not wrong. All right. I want to describe something that I'm less concerned you actually know how to like calculate and do, and I'm more interested in you understanding what's going on here conceptually, because it's an important piece of experimental evidence that quantum mechanics is happening. This is a picture of Arthur Holly Compton, taken in the mid-20s. Taken in the day when apparently creepy photographs were all the rage. He just looks creepy, doesn't he?
Looks like a supervillain.
Yeah, like a supervillain, right, from the 1920s and 30s. Is it the Hitler stash? Is it the eyes? Is it the grimace of teeth?
It's that mixed with the shadows of the eyes.
Yeah, the shadows of the eyes. So Arthur Holly Compton, by all reports, in an age when, well, white males are still stupid, but when there was nobody that was giving a voice to women in science or minorities in science, he was out at the forefront. Just a nice guy. And really worked to include kind of an international flair in his labs, where he worked, where he taught. He was in an age when it was not popular to encourage diversity. He was really out there. Like I said, this is like the 1920s and 30s, right? When to be hip in science, you believed in eugenics and a bunch of other weird stuff. Anyway, we're not here to talk about weird Hitler mustaches or creepy guys. Compton was studying something called scattering. And scattering is an optical phenomenon. Here's some examples of scattering taking place. This is probably the worst picture I could be showing because today is Earth Day, right? But this is smog and pollution. I believe this picture was taken in Indonesia on a really, really bad air day there. You can see the buildings are obscured by the haze and the smog. But this is an excellent picture to demonstrate scattering. Scattering is when light hits particles in the Earth's atmosphere. The light gets absorbed and then re-emitted kind of in all directions. And so when you've got a lot of particulates in the air of varying sizes, you get scattering happening all over the place, and it becomes like a white and sometimes brownish color. the phenomenon of scattering is really, really well understood. This is a picture, this is a better picture. This is a picture of the Great Smoky Mountains in the Appalachian. Okay, I'm gonna use the term mountains very loosely here because the Appalachians are not what I would consider mountains. Anybody who's ever been to the East Coast and seen them, I wouldn't blame you for being confused that they are hills because they're just not very pokey. It's not like we have mountains out here. Anyway, okay, these are Great Smoky Mountains. So called because from early on in the establishment of this country, this area is prone to high humidity and haze. And so the mountains were called the Great Smoky Mountains because it always looked like there was smoke on them. It wasn't smoke, it was just this atmosphere of water vapor. Nowadays it's more pollution and smoke and all that kind of stuff. But again, this is very well understood. And the reason I'm showing you this picture is because I'm lying to you slightly. This is actually not the Great Smoky Mountains. This is a computer simulation of the Great Smoky Mountains. And you would be hard-pressed to tell the difference between this picture and an actual picture of the mountains at sunset because we understand the nature of scattering so well. Arthur Hawley Compton was working on understanding scattering at its basic level, and he was running into a problem. It's a little bit similar to the problem that Max Planck had, in that the predictions that optics, Maxwell's equations make about scattering, the theoretical predictions, were not matching up with what Compton was experimentally measuring. And so he set out to try to figure out why. And it turned out for certain frequencies of light, you couldn't treat the interaction of light with the atmosphere in terms of its wave-like nature. The wave prediction wasn't matching the experimental results. And so when Compton took a page out of Einstein's book and said, okay, well maybe light, being this wave-particle duality thing, right? What if I treated this wave coming in not as a wave interacting, but as more like a billiard ball, more like a conservation of momentum problem? So he takes the momentum of light. Remember that Albert Einstein showed that light has momentum? And so using sort of that relativistic framework, Compton was able to show that you need to treat light like a particle to be able to explain Compton scattering, this particular weird mismatch between what's measured in nature and what classical physics would predict. So it was Compton scattering that started convincing more and more people that Einstein's formulation of energy and matter and the fact that light can have momentum was worth investigating even more. And then we get to, this guy. This is Louis de Broglie, and I pronounced that correctly. And I know that I pronounced that correctly because I was required by my first quantum mechanics teacher that I had ever had in college, okay? Dr. Francois van Hule, and we had to pronounce his name correctly, was from Belgium. Fantastic guy, wonderful teacher, good man. He demanded that we, so I don't know if you know this, but Belgians are like really particular about two things. Number one, that you do not confuse them with French people, okay? And number two, that you pronounce everything correctly. Like if you think the French are sort of like really like, ooh, you better pronounce that correctly or we're gonna kill you, the Belgians are 10 times worse, okay? And it's like this national identity. Pronounce it correctly and don't confuse us with French people. So Dr. Van Hule not only demanded that we pronounce his name correctly, but that we pronounce this guy's name correctly. This is Louis de Broglie, who was the Crown Prince of Belgium. This name is not pronounced de Broglie or de Broglie or any of those other formats that we would want to do in the United States. It's de Broglie. And Mr. Van Hule, we had 3 exams the entire semester. That was it. That was our entire grade. Every exam had a written and oral component. Every exam we had to go into his office, and for a half hour he grilled us and we had to answer orally, right? He told us, and he was true to his word, first question on the oral exam for the first exam would be, how do you pronounce this guy's name? You get one shot. We practiced a lot. Okay? We didn't understand anything else about quantum mechanics, but by golly, we were going to pronounce this guy's name right. Okay, so why are we talking about him? He's the Crown Prince of Belgium, okay? And he goes to college, their version of college back in that day, to learn how to become a king. So like political science and philosophy and classics and economy, whatever. King 101 or whatever it is, okay? And he gets his bachelor's degree at college in all this stuff, and then decides that he's not interested in any of that. His dad's still alive, so he doesn't have to be king for a while. And he goes back to school to become a physicist. Like he wanted to be a physicist. So he gets his bachelor's degree in physics, and then he goes on and gets his doctoral degree in physics. And what I'm about to present to you is his doctoral thesis, okay? This result, his hypothesis, this guess, is going to win him the Nobel Prize in 1929. This is the only contribution he made to the world of physics. Like after this, he more or less kind of disappeared. He'll show up at a conference here and there, but he either gets sucked back into the world of preparing to be a king or whatever, he goes off and does it. It was almost like he was a bit attention deficit on the world stage or something, right? And we will be forever grateful to Louis de Broglie for his contribution, what I'm about to show you, okay? But as far as going on and doing anything else, whatever he did had nothing to do with physics. What did Louis de Broglie do? You're going to look at it and you go, well, Mr. Bailey, anybody can get a Nobel Prize, right? Okay? So this is what Louis de Broglie said. He said, okay, well, Einstein told us that the energy of a photon, right, is equal to Planck's constant times its frequency. And since it's light, we can trade that frequency, right? Since the speed of a wave is equal to wavelength n, right, and the speed of light, right? Then we solve that for the frequency. We'll get c over lambda, which allows us to write down the energy of a photon either in terms of the frequency, which is associated with particles. I mean, frequency of a mass bouncing up and down is a very particle-y thing. But we can also write it in terms of wavelength, that obviously is tied into wavelength. This is the wave-particle duality of light that Einstein showed everybody is there, and that Compton is reinforcing. And so this isn't anything new. This isn't even worth a PhD in physics, okay? And then de Broglie said, well, remember, Einstein taught us that light has momentum. I did that demonstration, right, where I had that light bulb with the vanes in it, and I shined the light on it, and the light caused the vanes to speed up. There was a transfer of momentum between the photons of light from the light bulb and the vanes inside of that vacuum tube. And so Louis de Broglie is sitting there going, okay, all of this is true. He believed Einstein's result for the momentum of light. And he's like, I can put these together. Right? We put these together. The energy is equal to hc over lambda. And then I divide that by c. And I have the momentum, and we can kind of rearrange, and the c's cancel. And so the wavelength is going to be equal to Planck's constant divided by the momentum. That was his PhD thesis. And you're like, okay, I want a PhD in physics. I can do that. This is just math, right? It's more than math. Louis de Broglie believed, Einstein, Compton, others who were doing all of this stuff, right? He seriously believed in the wave duality nature of light. And then he was the first person to suggest, hypothesize, and show, theoretically, that if it works for light, it could also work for matter. De Broglie's hypothesis was, this isn't just wavelength and momentum of light. The result up here, Planck's constant divided by the momentum, is for any object that can have momentum. And classically, momentum is mass times velocity. And so Louis de Broglie hypothesized and suggested that if this works for light, it also works for electrons. He would be proven right 8 years later in experiment. I've already showed you the results of that experiment, the Davidson-Gurmanson experiment where they shot electrons at a double slit and it ended up interfering, right? And then he would win the Nobel Prize. So he got his doctorate for this, right? And then got the Nobel Prize awarded for that doctoral thesis when it was experimentally determined to be true. What Louis de Broglie is saying is anything with momentum has a wavelength. Doesn't matter if it has mass or not. What is your wavelength right now sitting here? I'm not moving, so what's my momentum? 0, right? And so if I take Planck's constant, which is a very tiny number, and I divide by 0. Divide by 0 in physics doesn't mean what it means in math, right? We divide by a very small number, we get very big numbers, right? So divide by 0 here for something that's not moving means the wavelength is infinitely big. In other words, the wavelength is bigger than the size of the universe, so it doesn't exist. There's no wavelength for things that are not moving. But if I start moving, do I have momentum now? Okay, so I have a non-zero momentum now. And we're going to take my momentum, take Planck's constant, divide by my momentum. That means I'm going to have a non-zero wavelength. Can you guys see my wavelength? No? No? Okay, well, let's figure out why. So let's do the, I went and found out how fast baseballs go. Okay? So we'll use a very American sport of baseball. Let's say that we've got a baseball that's moving at a speed of, I wrote down 45 meters per second. So that's like a 100-mile-an-hour fastball. So this is like major league pitcher speed. The mass of regulation baseball I looked up was 145 grams. So 0.145 kilograms, okay? So we're going to calculate the wavelength of a baseball. It's going to be Planck's constant, which I'm going to use in its joule seconds form because I have something that's has a mass in kilograms and moving in meters per second. Okay, so this is all standard joule stuff. Standard energy stuff. So that's 0.145 times my velocity 45 meters per second. And since I'm in joules and seconds and meters per seconds and kilograms, and I'm solving for a wavelength, I'm guaranteed to get this out in meters. This is 1.02 times 10 to the minus 34 meters. What kind of number is Planck's constant? Really big, really small? Super small, right? And the momentum of a baseball, right, compared to Planck's constant Planck's constant wins, right? It's 10 to the minus 34 divided by something that's less than 100, right? So the wavelength of this baseball is so tiny. So just to give you an idea, the smallest thing that we've ever been able to measure, the smallest distance we've been able to measure is 1/10,000th the width of a proton. That's like the limit of our human ability with our tools to measure things that small, right? That size, so take a look at one of your hairs, or maybe somebody else is a little bit more convenient. Okay? Depends on the length of your hair, right? So if you look at one of your hairs and you consider that, okay, to be 1/10,000th the width of a proton, then the proton to scale would be the size of the Earth, right, in comparison, right? And that would be just the proton that's down inside of a nucleus. Like it's hard to imagine, right, how small 1/10,000th the width of a proton is. That's approximately 10 to the minus 17, 10 to the minus 18 meters. This wavelength is trillions of orders of magnitude smaller than that. And so if your brain broke on trying to even just know what a proton size was, let alone 1/10,000th the width of a proton, right? Your brain definitely breaks on it. In other words, it's impossible for our technology in the state that it's in right now to measure the wavelength of a baseball. In other words, the wavelength of a baseball doesn't matter. It's so impossibly small, it's not going to do anything. But if we try to measure the wavelength of an electron going at 45 meters per second, well, Planck's constant, I don't know, 34 joules. And then the mass of the electron in kilograms, 9.11 times 10 to the minus 31 kilograms. And then 45 meters per second, okay? This turns out to be 7.28 times 10 to the minus 11 meters. Which is very solidly within the realm of our ability to measure. And so as far as we are concerned, everyday objects like baseballs and dogs and you and me and cars and whatever's moving, we don't see its wave-like nature. The wavelengths are too small. But for electrons and protons and neutrons and things that have very small masses, right? Their wave-like natures are very definitely measurable. And so we need to consider what's going on when we're dealing with electrons and protons and neutrons and hydrogen atoms and things like that. Quantum mechanics is the mechanics of the very small, dealing with those atomic structures. It doesn't happen, it happens, but it simplifies down. The wavelength comes out and doesn't matter, and so we can determine everything classically, a la Newton and Maxwell and everything else. It's when we go and we start dealing with electrons and dealing with protons and dealing with neutrons that we run into these barriers and have to deal with their wave-like natures. So Louis de Broglie pioneered this idea that everything has a wavelength, not just things that are light, but anything that has mass could have it too, and it can be found and it can be measured, and it was. He also gave proof to that phrase. Hey, are you and I on the same wavelength? Because we are if we have the same momentum. What else can we do with de Broglie's hypothesis? This is a drawing of something called a scanning electron microscope. Electron microscopes are used to take pictures of very, very tiny things, and they can do what optical microscopes can't. Optical microscopes, sort of like maximum magnification, you kind of bottom out around the size of like a cell. Like you can kind of tell the nucleus of a cell from a microscope and the mitochondria maybe, but you certainly can't see the DNA, right? Or the individual molecules that make up the structure of the cell or that kind of stuff. And that's because visible light is limited by diffraction. Light being between 400 and 700 nanometers, as soon as you start to try to look at things, they're about 1,000 nanometers across, light is going to start bending around them. Rather than bouncing off and giving you any resolution, diffraction means that the light will just bend around those structures. And instead of coming back to your eyes, it will get lost. Electrons, with their really tiny wavelengths, don't have that problem if you want to go take a picture, say, of DNA or anything else, okay? So by taking advantage, literally, using magnetic fields like lenses for these charges, using the wavelength of electron microscopes don't work if you consider electrons to be particles. Because particles can't be focused. But electrons, if they have wavelength, are waves, and waves can be focused, just like light can be focused. And so the device can be used to image things at incredible amounts of detail. This is a really gross picture of a dust mite, okay? But it really shows sort of the resolution you can get. The other thing about an electron microscope is they have really good depth of field. In a regular microscope, it's very narrow depth of field. Like you can like focus on different layers in the slide, but it's like one layer at a time. Electron microscopes can see incredible depth from down on the table all the way up to where the dust mite is and all that kind of stuff. But this doesn't even come close to the resolution that electron microscopes are capable of. This is a picture I got off the internet. I had to turn it on its side so we could see what's going on here. Over here, this is a snowflake. Okay, so and snowflakes we can see in regular microscopes, right? No big deal. It's hard to see from where you're sitting, I know, but there's these little boxes in each of these pictures, and then basically the next picture is the zoom in factor, right, of what they're doing. They start over here. From this picture to this picture represents a, 12,000 times increase in the magnification. We started over here with the structure of the snowflake, and we ended up here almost being able to see the individual water molecules that are making up that snowflake. Electron microscopes are very capable of seeing things that are very small, and we use De Broglie's hypothesis and take advantage of it in a very real application. This picture is going to be a video, and as soon as I hit play, it's going to start zooming in. This is a series of pictures that were taken by an electron microscope, put into a video. Each of these little dots is a simulated red blood cell. They're actually little glass beads that were produced, to be the size of a red blood cell, so that you understand the scale here, right? So watch how far they can zoom in on these little glass beads. Again, each one of those little spheres is the size of a red blood cell. Right? Well, finally stopped. Right? Okay. That's that extreme, like an optical microscope, right, can barely make out the presence of a red blood cell, right, okay, as just this sort of blob, right? Electron microscope can keep going. This one didn't even go as far as they're capable of. I think the record, I looked it up this morning, it was 0.01 nanometers or something like that. 1 billion, 10 to the minus 9, so this is 10 to the minus 10, 11-ish meters on the scanning electron microscope before they hit the diffraction limit. It's really, really impressive. Very, very impressive. I did this example already with the baseball and the electron moving at 45 meters per second. I just want to point out, if you ever run up against an example or a problem in your homework or otherwise, I wouldn't do this to you on a test because I think it's especially mean, but you see how that speed right there is being written as a fraction of the speed of light? Okay, just like we did in relativity. That is a giveaway that you have to calculate the momentum of this electron as gamma mv, the relativistic momentum. So if you're watching another YouTube video or something like that and you see somebody drop gamma into the calculation of momentum for an electron, it's probably because it's moving so fast that you have to make the relativistic correction for its mass increase. Remember how mass increases with speed? Okay? So just realize that if you ever given information about the speed of something as a fraction of c, relativity is hiding somewhere, right? And you probably have to calculate, in this case, the relativistic momentum. Okay. Just to warn you. All right. How do we come to grips, okay, with what we've learned so far, and especially come to grips with something that could be a wave and a particle at the same time? This can be difficult to conceptualize or like hold in your hand. Like, what does that look like, Mr. Balogh? What does a wavicle look like? Okay, so we have an answer, and it's not gonna. Remember how we cheated and we used electric field lines? Remember Faraday's lines of electric force, right? We had those pictures of the field lines and it gave us an idea of what the electric field is real, the pattern of forces is real, but the lines don't exist. But there's such a good visualization for what's going on that we just hold on to it. Even though we know that things aren't connected by lines, we still use it anyway. What I'm about to show you is the same thing. This is not how it actually is, but it's a good analogy or construct for us to sort of wrap our brains around when it comes to struggling with wave-particle duality. So you can see on the screen, I do have something that looks like a wave, right? I mean, there's wavelength here. There's wiggles up and down. I can measure distances between peaks. I can figure out the frequency, yada, yada, yada. But it's also particle-like in that this wave begins and ends. And while it doesn't have an infinitesimally small structure, it does have a very definite beginning and end, and so it's contained in a certain amount of space. In other words, I could draw an envelope around this structure. Can kind of imagine how this wave is being contained inside of this football-y shaped thing, right? And so this structure, mathematically and conceptually, has both wave and particle features. Wave in that there's wiggles and wavelength, particle in that it's contained to a specific amount of space. And we can say, well, it's like there versus over here. You know, regular waves, traveling waves are sort of infinite, right? They just go that way as far, that way as far, but we're trying to contain them into one place. And so this is a picture. I mean, a lot of physicists we kind of think of it this way, but we get into the math and it becomes a very different thing in our brains. But at this level, it's not a bad way to go. In terms of like, what's the picture in my head, Mr. Balogh? But this idea and this struggle, okay, can be described mathematically by putting together waves. We can actually build a particle by putting together waves of different wavelengths and frequencies. And I want to show you just a video of how this is going to work. Let me point out that the top graph up here is going to be what the waves look like in space. And then they've got down here another graph, which looks kind of weird. They got Planck's constant divided by wavelength. But de Broglie's hypothesis tells us that this is the momentum. So they're going to give you position and momentum for all the waves that they're about to show you. And you're going to see how infinite waves going on both directions as far as possible, can actually be put together to make a finite one.
A wave has an amplitude and a wavelength, but no beginning or end, and nothing like the definite position of a particle. That remains true if a wave of the same wavelength is added, either in phase or out. But if waves of different wavelengths are added, the resulting shape is altered. And if those wavelengths are close together, and especially if more waves of nearby wavelength are added, the result can be a kind of wave concentrated in a limited region of space.
Adding more and more waves of different frequency and wavelength, different momenta.
So with a range of wavelengths, and therefore a range of momenta, a wave-like object can be constructed in a fairly definite place.
A wave-like object can be constructed in a fairly definite place. This is why people go crazy when they study quantum mechanics, right? Because you kind of have to hold these things in your head, right? About wavy things that begin and end, right? And it flies in the face of what we've learned in classical physics. But nonetheless, I wanted you to see as they put those waves together how this became tighter and tighter, but we lost sort of resolution or definition when it came to understanding the momenta. There's a range of momenta that this thing has instead of a very definite momentum. So unlike a classical particle where we say it's right here and I know what its momentum is, a quantum system, something that has both wave and particle nature, we lose some definition on where it is and how fast it's going. This idea about how quantum systems work and how there's an interplay between how much we can know about where the particle is and how fast it's going or what its momentum is called the Heisenberg uncertainty principle. This is a picture of Werner Heisenberg. The man knew how to rock a fedora. I mean, seriously, like, this is amazing, okay? He also knew how to rock a really big nose. It was always a joke amongst the physicists of his time that Heisenberg had the biggest nose of all of them. Heisenberg was a German scientist. During World War II, he worked for the Nazis on their version of the Manhattan Project, the atomic weapons program. He himself was a Nazi and was one of the foremost nuclear physicists, quantum mechanics of his time, and continued to be after the war. He was captured at the end of the war by the Americans and the Allies, brought to America, given amnesty, and worked on the American nuclear program for the rest of his career, and then retired and settled in America. He and several other scientists were very big in quantum mechanics and nuclear physics before the outbreak of World War II. I mean, Einstein was in Germany until the mid-1920s. Einstein kind of saw the writing on the wall and moved to America before the Nazis would come to power, significant power in Germany. And being Jewish, Einstein knew that he had to get out. Heisenberg wasn't Jewish. Neither were a lot of the scientists that stayed on. Any Jewish scientists either fled or were captured and put in concentration camps. But the historical evidence surrounding the Nazis' bomb project, a lot of that evidence was destroyed when the Nazis fell. They took their secrets with them, burning their records, all that kind of stuff. Lisa Meitner was a German physicist. She was the first person to experimentally discover nuclear fission and never got credit for it. Her work scared the American scientists into the idea that the Germans were onto the ability to make nuclear weapons and something needed to be done, which is what started the Manhattan Project in the United States. We'll get more into the Manhattan Project and nuclear weapons and things when we get to nuclear physics. The reason I'm telling you this story is that the German scientists like Heisenberg who were captured would never admit publicly to this. But there is enough historical evidence to suggest that Heisenberg and others in the German hierarchy were actively working to sabotage the German weapons program. Heisenberg is a leader in the field of quantum mechanics at the time. And the records show the Germans making mistakes in their calculations that would convince their leaders that atomic weapons were not viable and that the Americans couldn't possibly be making atomic weapons because it was a theoretical impossibility. And Heisenberg and others knew better. They knew exactly how to do it. And the fact that they never reported that and actively made sure that people in the decision hierarchy believed that it wasn't possible, it is certainly conceivable that Heisenberg and others are the reason that the Third Reich lost. Because a lot of the money and development was channeled away from the nuclear weapons development into like the rocket V2s, the terror weapons that were splashy and expensive, but they weren't something that were going to win the war for Germany. So, and I want to make it very clear, I do not support Nazism in any way, shape, or form, right? And I'm not praising Nazis at all. I'm just saying that people aren't always what they seem on the surface or what they feel like they have to say in order to make sure that they can get their work done. And it's very possible that people with cool hats and big noses could be heroes in ways that we didn't expect. Anyway, Heisenberg came up with an idea, this concept surrounding this wave-particle bundle, and it is probably the most unfortunate Google Translate mistake in history, okay? In the age before Google Translate even existed, you had translators that just kind of did their best. Now, human translators are still better than Google Translate, although it's coming close. We're getting really close now, right? But Heisenberg was German, and so he was writing in German about this idea that you can't know everything about the position and momentum of a quantum particle. And so Germans have this thing for inventing words. They love inventing words, right? Especially when it comes to like place names. Like they'll name a town like the place where the rabbit killed the goat or whatever, right? Okay? And it'll be like, right? Like it's just this huge long concatenation of sounds, right? Okay? This big long name. So the word that Heisenberg used to describe this principle did not have a translation into English. And so the English translators chose the next best word, which was uncertainty. If we had to do it all over again, and this isn't a word, and I don't think this appears in the dictionary, but the word that Heisenberg used in German most closely translates to unknowability. So it's Heisenberg's unknowability principle. But unknowability is not a word in English, right? And so translators of the time chose uncertainty. Now the problem with the word uncertainty is it makes us the butt of jokes. Oh, look at those physicists, even they say they don't know, right? Okay, because certainty implies that you absolutely know something, okay? Physicists are absolutely sure that this is true. Okay, we've measured this phenomenon, right? So we're darn certain that the Heisenberg uncertainty principle happens. But Heisenberg's unknowability principle is all about a trade-off in what we know about position and what we know about momentum. Mathematically, it's described with symbols that are going to hurt. And it's going to hurt in several different ways. Let me try to explain. The deltas you see on here are not the deltas you know. So the deltas you are familiar with are like final minus initial, right? That's not this. This delta is talking about the uncertainty in a measurement. So let's say, okay, that we have an uncertain, let's say that we're watching a volleyball game and a player rushes up to the net to spike the ball, right? The ball's coming through and they jump up and they spike that ball back at the opposition, right? And somebody on the court's got a radar gun and they're measuring the speed of that volleyball after it gets hit, okay? And let's say that the speed of this volleyball, okay, is measured to be 35 meters per second. Now, we're kind of used to, in class, of just kind of knowing what the velocity is, and we don't really worry about the certainty in the measurement, the uncertainty in the measurement. But every device comes with an inherent ability to measure. In the case of this example I'm doing, we're going to measure that, we say that it's 35 meters per second plus or minus 5%. In other words, the device is being used to measure how fast this volleyball is going, can measure, finds the measurement to be 35 meters per second, but it could be off by 5% in either direction, right? So whatever 5% of 35 is, it's 5% of 35. 0.05 and 35, so 1.75, right? So this is, the speed could be 33.25 or it could be 36.75, right? Like it's somewhere in that range. There's always going to be this plus or minus value. It's probably in the middle, but the error bars are set. So this uncertainty, this plus or minus 5%, that's the delta x. The uncertainty in position, right? The delta x is 0.0, or the uncertainty in the measurement here, so not position, this is momentum, because momentum is mass times velocity. So the uncertainty in that momentum is going to be mass times the uncertainty in the velocity, okay? And so this velocity's uncertainty is this 5% of this thing. That's what this notation means. I'm going to give you an example of calculating this in a second. Notice that the product, the multiplication of the uncertainty in the measurement of position and the uncertainty in the measurement of momentum always has to be greater than or equal to a constant. Planck's constant divided by 4 pi. Here's my second warning about this. You are going to see in your book, on YouTube, you'll see me do it. I apologize in advance. You will see the uncertainty principle written as h bar over 2, because h bar is shorthand notation for h divided by 2 pi. The factor of 2 pi shows up in quantum mechanics so much that physicists got mad at having to write it down all the time, and so we just invented a new symbol, h bar, okay? So h bar over 2 would be equal to Planck's constant divided by 4 pi, but you will also see it written as greater than or equal to h bar, without the 2 on it. You are being caught in the middle of physicists arguing over where is 0. I'm hiding 2 semesters worth of very messy math that involves a lot of statistics and some other things, okay? But when it comes to the Heisenberg unknowability principle, you can kind of put 0 wherever you choose, and there's 2 places that we argue over where it should be. Sometimes you get a factor of 2, and sometimes you don't. I am not going to care if you are a factor of 2 off in these calculations. It's just not worth it to me for you guys to learn why this pissing match is happening, okay? Just know that if you see somebody solve a problem and they're off by a factor of 2 from the way you're doing it, they just are probably in a slightly different system, and that's okay, right? I'm not on an exam, if you've written down one of these or you saw an example on your favorite YouTube channel or whatever and you do it that way, and you do it right, I'll give you credit, right? Okay, so Wiley Plus will be very particular, of course. I've done the h over 4 pi, which is the way your book does it, but that's no guarantee that the graduate student that programmed Wiley Plus used h bar over 2, right? They might not have, right? So just realize, if you're getting a wrong answer, try dividing by 2 or multiplying by 2 and see if you get the right answer. It might come out. I apologize for this. I wish it wasn't this way. I wish physicists could just agree, right, on where to put 0 for this, but for some reason we can't. So you're just caught in the middle. Let me show you an example of calculating the uncertainty in position of a volleyball, and then I'll do it for an electron. So our volleyball is moving at 35 meters per second, plus or minus 5%. We're going to calculate the uncertainty in position, which is going to be greater than or equal to Planck's constant divided by 4 pi divided by the uncertainty in the momentum. The uncertainty in the momentum will be mass times the uncertainty in the velocity, and that's going to be 0.05, the percentage, times the mass of the volleyball. I went and looked this up. The mass of a volleyball is 0.350 kilograms. So 5% of 0.350 kilograms times 35 meters per second. So here's my momentum, here's my delta on that momentum, because it's the delta on the velocity. And this is equal to plus or minus 0.613 kilogram meters per second. So that's my uncertainty value. And that's the value that goes into this calculation right here. So delta x, the uncertainty in position, would be measured as Planck's constant, 6.63 times 10 to the minus 34, all divided by 4 times pi times 0.613 equals, and I got 1.72 times 10 to the minus 34 meters. Okay. What does this say? We don't know what the speed of this volleyball is to within 5%. Which means, according to Heisenberg's unknowability principle, we don't know where the volleyball is to within plus or minus 1.7 times 10 to the minus 34 meters. In other words, do we know where the volleyball is? Absolutely. Like 10 to the minus 30, we can't even measure past 10 to the minus 17, right? We know exactly where this volleyball is. This breaks, this is broken for normal everyday object. This is absurd. It's stupid. I shouldn't even done this calculation. But I wanted to show you that Planck's constant is an impossibly small number. So even if we don't know very much about, we're pretty certain, 5% seems to be pretty certain. We can be very certain about where something is, regardless of uncertainty in momentum. But what if we did this for an electron? So for an electron that has a mass of 9.11 times 10 to the minus 31 kilograms, moving at a speed, again, of 35 meters per second, then the uncertainty in momentum for an electron, 5% of the momentum, 31 times 35 meters per second, gives me 1.59 times 10 to the minus 30 kilogram meters seconds, plus or minus. And so now when I go to calculate the uncertainty, I'll take Planck's constant divided by all these numbers I've got. For the electron, this turns out to be 6.64 times 10 to the minus 5 meters. Can we measure 10 to the minus 5 meters? This is like 66 microns. That's like slightly bigger than your hair's width, which is dead easy for us to measure. That number right there is 100,000 times bigger than the radius of an atom. So for the nucleus of an atom, if a nucleus looking at an electron goes, the electron's going fast, but plus or minus 5%, they know a lot about how fast that electron is going. They're 95% certain how fast that electron is going. But you lose a lot of definition as to where that electron is located. For an atom, they don't know where the electron is if they know how fast it's going, and vice versa. If you know where an electron is, then you have no idea where it came from or where it's going. Like if I know that an electron is right here, like 100% certain it's right there, I can tell you nothing about how fast it's going. I can't tell you about its direction. I can't tell you about its magnitude. If I know that an electron is moving at 9/10 the speed of light from there to there, I cannot tell you with any certainty where it is in that space. Fundamentally, our universe is put together in such a way that we can't know everything about everything. There is always a trade-off in knowing where something is versus how fast it's going. And there's a similar concept of the Heisenberg unknowability principle when it comes to energy and time. We won't get into that one, but just so you know, this completely flies in the face of classical physics, where we know everything about everything, right? This is saying that you can't know everything. You always have a price to pay. There's a trade-off in the amount of information that you can have. All right. That's the end of chapter 29. Okay? And I'm gonna get started here on chapter 30 because I wanna leave you with a cliffhanger. Always leave them wanting more, right? But it's gonna set us up for tomorrow to be able to focus on the quantum mechanical model of the atom. We're going to talk atomic theory. I'm going to take you very quickly through the first couple modern theories of how atoms worked. And we're going to start with J.J. Thomson and discovery of the electron. So we're backing up a little bit in history. So you'll notice Einstein, 1905, right? De Broglie in the 1920s. Like we were doing kind of the beginning of the 20th century there. Now we're kind of reversing back into time right before Einstein, and we're going to come up through it. So all of these things that I'm describing to you, relativity, quantum mechanics, all this, it's happening simultaneously, right? Through all of these different avenues. But J.J. Thomson is the first person to discover electrons. We didn't know electrons existed until 1897. Okay, like it seems so recent, right, in history when you consider that chemists were playing around with chemistry in the 1600s, right? It kind of blows your mind that we really didn't know. And it really wasn't until 1906 that we actually knew what the charge on the electron was compared to, we always had this ratio before that, but we didn't really know separately what the charge on the electron was and what its mass was. But J.J. Thomson was a good British citizen, and based on his experiments with cathode rays and discovering electrons, he was the first person in the modern era to posit or to hypothesize what atoms might look like. And based on his measurements, he came up with what he called the plum pudding model of the atom. Plum pudding, have you ever had bread pudding or rice pudding? It's kind of like you like mix it all up and it's like a gooey thing, and then you bake it for a while and it becomes less gooey, but it's still gooey, right? In Britain, they would do, instead of rice, they would do bread and like milk, and they kind of mix it up, and they would put dried fruit in it. If you've ever had a fruit cake is a dry version of a pudding. Anyway, in Britain, they would make their bread pudding and then they would put raisins in it. And for whatever reason, I'm not responsible for the British, we kicked them out in 1776, I don't care. They call the raisins in pudding, they call them plums. They also say aluminium, but anyway, okay? This is his model. His model is positively charged goo, which is the pudding, and then electrons, like raisins in plum pudding, okay, are these little negative bundles inside of this big gooey mess, right? That was his model of the atom. And of course, we poke fun at it today, like, oh, that's stupid, right? But again, remember, Thomson didn't have hindsight, right? Einstein had not come along yet, right? And all this kind of stuff. So it's significant in that Thomson discovers the electron and comes up with the first model of the atom, albeit being very wrong. So how do we correct this? We back up 1 year. And we talk about Henri Becquerel and his greatest discovery. How many of you have ever heard of Henri Becquerel? That's what I thought. Okay, nobody knows who Henri Becquerel is. Because his greatest discovery was not a thing, it was a person. Henri Becquerel is the poster child, as far as I'm concerned, the poster child for the scientific method. if you want to know that the scientific method works, study the life of Henri Becquerel. The man was wrong all the time. Like, all the time. His hypotheses were just wrong. But he kept at it. He would make a hypothesis, test it, realize it had all gone wrong, come up with another one, test it again, and by golly, he would finally get somewhere, right? But wow, Murphy was not kind to this man, okay? Like, he just guessed wrong all the time. But he persevered, and he always tried. And so he would win out in the end. In 1894-95, a friend of Becquerel's would send him a package, and in this package would be a rock. And in that rock was called pitchblende, and it was an interesting rock because it was mined out of a mine in Romania, and it generated its own heat. Like, the rock would remain warm, regardless of whether it was like in the sun or in the snow or anything like that. It was just sort of this thing, the magical properties of this rock out of this mine in Romania. And he sent it, Becquerel's friend sent it to him thinking that Becquerel would be interested in studying, because Becquerel was like studying everything. And Becquerel at the time was really into taking pictures of leaves. He had this idea that he could take a photographic plate, a black and white photographic plate, and he could put like the leaf of a tree on it. And if he set it out in the sun and the sunlight shone through the leaf, he could get like a photo negative of the leaf structure on the photographic plate. And then he could study that. Like it was like a very rudimentary X-ray, right? Okay. But it wasn't X-rays, it was sunlight. The whole thing didn't work very well. Okay. And so Becquerel was like working for like the better part of 2 years on this thing. And I'm not a believer in coincidence, okay? But as fate would have it, Becquerel would take this rock sample and place it on a shelf to study later. And that shelf was right next to the cabinet where he stored the photographic plates that he was using for his leaf pictures, okay? And these plate cabinets had to be sealed from the light, like a dark room, right? They didn't want any light going in there because the plates would get exposed to the light and they would not be useful. And then fate intervened and gave Paris, France, a couple weeks of cloudy weather, just like solid overcast. And Becquerel was like disappointed, right? Because he couldn't do his little experiment where he, put his plates out. He needed direct sunlight, right? And so he would come into the lab and he'd like wait for a break in the sun and he'd run out, right? Get this right. It would never stay around for long, and so he'd go back in dejected. A couple weeks went by. Finally, a bright, clear, sunny day. Becquerel rushes into the lab because he can put all of these plates out. He reaches into the cabinet and he starts pulling plates out, and he notices that they're already exposed. Like they've already been like partially put in the light. And so he's kind of disappointed because he can't do his leaf thing, right? And he's checking the cabinet, right? Like he's looking for leaks, like did light come in? He goes and asks the lab assistants, did you guys leave this open? No, we haven't touched it, right? And he's sitting there trying to figure out, and he notices that the plates on the left-hand side of the cabinet are all like most exposed, and then as he goes through the cabinet, the plates on the right-hand side are less exposed. And he's sitting there, and he's just trying to figure out what the heck went wrong, when he realizes that sample of pitchblende is sitting there right next to the cabinet, right? And he looks at the pitchblende, and he looks at his plates, and he looks at the pitchblende, and he looks at his plates. He reaches up and he grabs the pitchblende. He looks at it. He walks out the door, down the hall, third door on the right, knocks on the door. The young lady answers. And he hands her the piece of pitchblende. He said, "Marie, I think you might be interested in this." That was Marie Curie's first sample of radium. Pitchblende was an ore that contained a lot of radium. The world would never be the same. Henri Becquerel's greatest discovery was Marie Curie. Okay? Marie would take that sample and with her husband Pierre in that lab, start working on trying to isolate the thing that caused Becquerel's plates to go cloudy. And they would work tirelessly for the better part of 3.5 years, continuously applying chemistry and other things to isolate this thing, this element that was in the pitchblende that was giving off this radiation that they couldn't see. To this day, you cannot study Marie's notebooks for more than a half hour at a time before you have to take a break and get out of the room so that you are not exposed to too much radiation. Marie and Pierre would discover radioactivity. They would isolate radium. Marie would become the first woman to win a Nobel Prize and the first person to win 2. There have only ever been 4 people that have won 2 Nobel Prizes. The other 3 were men, and the second prize was always the Nobel Peace Prize. Marie Curie is the only person to have ever won 2 science Nobel Prizes. She was incredible. She wasn't perfect, and she lived a very colorful life. But boy, did she have her science down. Marie would go on to fund the first women's university dedicated solely to STEM majors. She would do other things in the field. The first Nobel Prize was for chemistry for isolating radium, and the second Nobel Prize was for the discovery of radioactivity. Tragically, Pierre's life would end too early. Marie's continued on. She died fairly old. No evidence that she died of radiation or cancer or anything like that. But Pierre would die one day coming home from the laboratory, having bought a bouquet of flowers for Marie. And he would not be paying attention to what he was doing, and he stepped in front of a horse and was run over by the carriage. According to everybody that knew them in their own letters, they were madly in love with each other. Theirs was a perfect union of mind and heart in their quest for scientific discovery and the love that they shared. Probably the best scientific couple that has ever existed. They discover radioactivity in 1896, and a New Zealander, a Kiwi from the land down under, would take up the baton and use their discovery of radioactivity to start probing the atom of gold. What Rutherford did is he came up with experiments. He was trying to verify Thomson's model of the atom. And it was becoming clear in some of these experiments that Rutherford was doing that Thomson's plum pudding model of the atom wasn't right. Rutherford was taking pieces of gold leaf foil. This is extremely thin, pure gold foil, like aluminum foil, but just very, very delicate, like tissue paper, even thinner. And he was firing the Curie's radioactive particles, alpha particles. They identified alpha, beta, and gamma radiation. He was taking alpha particles, which are the nuclei of helium atoms. And he was firing them from an alpha source at the gold leaf. And you know, if Thomson's model was correct, you would expect these alpha particles to kind of tear through that foil and like tear it up. But that's not what was happening. The alpha particles were sailing straight through the gold foil and not affecting it at all. In fact, every once in a while, one of the alpha particles, instead of coming straight through, would come out at an angle. And they were able to detect the alpha particles on the other side of the gold foil with a phosphor screen. The only problem was this screen and the alpha particles that were hitting it gave off so little light that they had to set the experiment up in a dark room and close the door, no light can get in, and sit there for 40 minutes in the total darkness. No YouTube, no Instagram, no nothing, right? Except the sound of their own voice. Waiting for their eyes to get sensitive and dilate enough so they could see the faint flashes on the phosphor screen. Can you imagine what discussions might be like for 40 minutes while you're sitting in a dark room with nothing else to do, right? It must have gotten very boring. Well, it got very boring for Rutherford. He didn't want to have anything to do with this. It was interesting, but he didn't want to have to sit there and take the data. So he has this problem, right? What is the director, what is the person that has a PhD and is the director of the lab to do when you've got an experiment that needs to be done, but is boring to do? It's the easy answer. Find some graduate students, right? Graduate students were built for this. They were born for this, right? Like, you need lab rats, it's graduate students, right? So he threw some graduate students into the dark room, said, don't come out till you give me some data, right? And so these poor graduate students would sit in there for hours, right? Counting flashes on a screen, right? One of those graduate students was named Hans Geiger, who would later develop an instrument called a Geiger counter. It didn't count Geigers, it counted radioactive particles. Necessity is the mother of invention, isn't it? You can imagine Geiger sitting there going, I do not want to be in this room counting these things. Is there some way that I can make a device that would count them for me? And that's exactly what he did. And we still use Geiger counters to this day to count the presence of radioactive particles. Anyway, the grad students would notice that some of these angles of these particles were very big. And so they built the detector to wrap around the gold leaf onto the back. And to their utter astonishment, they detected alpha particles bouncing off the gold leaf foil. When Rutherford later would try to describe this in public lectures, trying to give an analogy for how amazing this was and how unexpected it was for alpha particles to be bouncing off of gold foil, he used an analogy that was pertinent to the day. At that time, World War I was kind of gearing up, everybody was making battleships, and battleships had huge guns on them. And so there was this thing known as the 16-inch gun. It was a cannon that fired a projectile that was 16 inches in diameter. So imagine a bullet that's 16 inches wide and about 2 feet long, okay? Hundreds of pounds of bullet, right? He says, imagine if I take a 16-inch cannon or 16-inch gun and I aim it at your face. So you're standing in front of the barrel, right? And the only thing you have to protect yourself is your handkerchief, your piece of Kleenex, right? That's all you got to block this cannon firing at you. And I fire the cannon. And to your astonishment, the 16-inch shell bounces off the piece of tissue paper. That's how surprised they were when they saw these alpha particles bouncing off the gold foil. It shouldn't have been that way, but it was. The alpha particles were like those big shells. The gold foil was like the tissue foil. It should be obliterated by it, but it wasn't. So Rutherford has to figure out why, what's going on. And so Rutherford deduces that the mass of an atom is mostly contained in a very small spot at its center. And he names that center the nucleus. And that's where we get the nucleus of the atom. He would later discover that there wasn't enough mass in that nucleus to account for just protons alone. So there had to be additional mass, but it didn't have any charge. And he would call the additional mass, the particles that made up that additional mass, he would call those neutrons. So you had protons that carried the positive charge, and then neutrons that had the mass of a proton but had no charge whatsoever. So that's where we get neutrons from. And Rutherford needs a model where 99.9% of the mass is at the center, but then you have some very small masses that are going around it, like orbiting around it. Is there something anywhere where 99% of it's in the center and then there's these little things that are going around? What's that sound like? Space. Sounds like our solar system, doesn't it? The sun takes up 99.9% of the mass of our solar system, and then there's just a few planets that make up the 0.1%. You are the 1%, right? Going around the outside. And so that's why he calls it his planetary model. He models it after the solar system, where the nucleus is like the sun, and the electrons are like the planets, okay? And the electrons are in orbit around. So this is the first model of the atom that contains this concept of the nucleus, and that electrons are in orbit around that nucleus. Rutherford coins this phrase, this thing called the atomic number. This is going to be very important for us moving forward. The atomic number counts the number of protons in the nucleus. It's a way of keeping track. Okay? And he calculates how big these atoms should be, and realizes that atoms have a lot of empty space in them. And one of the calculations you can do is if you just look at the tip of your stylus or the tip of your pen, like you just look at that lead or that little ball bearing or the very tip of your stylus, that's about 0.5 millimeter in diameter. If you hold that up and you look at it, and we scale, and we say that's the size of the nucleus of an atom, then Rutherford calculates that the closest, the innermost electron to that nucleus, right? If you're standing in the center of a soccer field or a football field, right? The midline, 50-yard line, and you look, and that's your nucleus at the tip of your pencil, the closest electrons are going to be in the end zones, or where the goalies are. And the next closest are going to be like in the nosebleed section, okay, of the stadium, right? And everything in between is empty space. I personally feel like the thing that's in between is olive oil, because olive oil holds the universe together, but that's just my Italian coming out. Okay? But like these are this is like kind of amazing idea, right? That atoms are mostly empty space. But Rutherford has the experimental evidence to prove it. But, and Rutherford wasn't done. He knew that there were problems. And this is where the big problem is, okay? Electrons moving around a nucleus in an orbit are undergoing accelerated motion. They're moving in a circle, so they're constantly changing their direction, and that's acceleration. We learned back in our section on electric fields and magnetic fields that when you accelerate a charge, it gives off energy. It gives off electromagnetic radiation. So according to Rutherford's model, electrons in orbit around the nucleus should be giving off electromagnetic waves, a la Maxwell's equations. If they're giving up energy in the form of electromagnetic waves, the energy of their orbits should be in decay, and they should be spiraling in and slamming into the nucleus. If you take a look at your thumb, and you wait a little while, you'll notice that your thumb is still there. Rutherford calculated it should take on order of like 10 to the minus 7 seconds for all the electrons to come crashing down into their nuclei. Obviously, this is not happening, right? Okay? Something is different when it comes to the atom. For some reason, the electrons in these orbits are stable. And Rutherford is not going to be able to figure out why. So he puts it to the scientific community. He publishes his model of the atom. And he says, I know there's problems here. We got to figure this out. Here's my experimental results. This is what I think. We've got to figure out what's going on here. Rutherford was a He was a bit of a bully, arrogant, very tall, sort of deep voice. People would always do what he said because he didn't threaten them, but he was sort of that threatening personality. And he had a particular dislike and disdain for chemists. He didn't really like chemistry or chemists. And he, in response one time, when somebody asked him about some chemistry question, he said, you know, physics is the only true science. Everything else is stamp collecting. He was throwing shade on chemists in particular. He believed that chemists, all they did was just like keep track of the elements and that was it, right? They were stamp collecting. They were filling out their periodic table, but there wasn't any true science to that because physics was the true science. Ernest Rutherford would win the Nobel Prize for his model of the atom. In what?
Chemistry.
Chemistry. I think that's the biggest FU chemists have ever given physicists in history, right? Because Rutherford would have to claim a prize in a science that he didn't want anything to do with. I'll leave you there, hanging on how to fix this. And we'll talk about it tomorrow when we get to talk about a Great Dane. See you then. If you want to stick around and do homework, that's great. You could probably do most of it on this chapter alone, let alone last chapter.